Welcome to another episode of the Mapscaping podcast. My name is Daniel and this is a podcast for the geospatial community. My guest on the show today is Konstantine Klemmer, and today on the podcast we're talking about Satclip. So Satclip is a model developed to encode geographic locations based on satellite images. It's designed to generate location embeddings, which are vectors of numbers that represent unique characteristics of a location as seen from satellite images. These embeddings encapsulate features that make a location distinct in terms of its appearance in satellite imagery. If all this sounds incredibly intimidating, don't worry. Konstantine does a brilliant job of explaining the concepts and the use cases for Satclip before going on to a broader conversation around local versus global models when we think of GeoAI. And if you're still struggling with this idea of vectors and embeddings and what they mean and how they're created, it's worth listening to this episode because Konstantine gives one of the best explanations of what these things are and how they work. Even I could understand it. So without further ado, here's my conversation with Konstantine about Satclip. Hey Konstantine, welcome to the podcast. It's great to have you here. I'm really excited about our topic today, which we'll introduce in just a second. But first, I think it's important for people to understand that you're a researcher and you're interested in this, or most of your work is around this intersection of geography and AI. And some people refer to this as GeoAI. That was a really brief introduction. Can you sort of add a few more words to that, please? Maybe help put your work in context as well. What is it that you do and where do you do it?
Thanks for having me. Great to be here. What is GeoAI and what do researchers in GeoAI do? I think that's a great question. It's an open question and there's many of us working on all sorts of different things. But I'm a researcher at Microsoft, famous big tech company. And so a lot of my research is very focused on big models and models that can at some point be very useful to people and that might be able to be great for business. I think there's lots of potential for that. So this is really the focus of my research. My story is a very interdisciplinary one. I have some research experience in economics, then in transportation, civil engineering, and now I ended up in machine learning. And so this interdisciplinary perspective and always having the focus on applications and on deployment and on needs of practitioners on the ground is really what drives my research. So I only want to research things that actually are useful in the real world.
Well, I really appreciate that. Sometimes I feel like there's a lot of great research and it's interesting, but where is the application? Like, is this just a solution looking for a problem kind of thing? So I appreciate that focus on things that people can actually use. And I realize that there's a balance there. Like there needs to be a certain amount of, just greenfield research where people just go out and try things in order to find out what could be applicable in the real world. But that focus, I think, is really important. One other thing I want to mention here is this focus on, you talked about big models. That's going to be interesting later on when we move on and talk about the topic of conversation today, which is something called Satclip. Because my understanding is that the actual model is not that big, but let's leave that for now. Let's introduce the idea of Satclip. What is it? How does it work? What can we do with it?
Yeah, so Satclip is a kind of culmination of the last 2 years of my postdoctoral research with some amazing collaborators at Microsoft and at Harvard and in Europe. And yeah, Satclip in short is a location encoder. A location encoder is a neural network that takes in as inputs geographic coordinates, so latitude and longitude, and then returns embedding, a vector of numbers. And that vector of numbers ideally represents some information we know about this location. In the case of Satclip, that information is learned from a large data set of satellite images. And so you can think about the location embedding of Satclip to represent features that make a location look unique on satellite images.
So you talked about a location embedding, so a location encoder. Would it also go the other way? Is it also an image encoder? I can put in a location and get a embedding out. Could I also put in a location and get an image out, or perhaps put in an image and get a location?
Yes, so the intuition is exactly right. The way Satclip is trained is using both an image encoder and a location encoder, except that you don't get an image out of the location encoder and a location out of the image encoder. Out of both, you just get an embedding. And I think now is a great point to explain a little bit what an embedding is, because it's really important to understand for what Satclip is, and it is in generally one of the absolute key concepts of current AI research and what makes these AI models across domains, from large language models to image models, so powerful. And an embedding is basically a representation of a data modality that is different from the original input dimensionalities. So if you think about an image as basically a matrix of, I don't know, let's say 64 by 64 pixels, and then 3 different channels, right? We have a red and a green and a blue channel. That is quite big. That is 64 times 3 data points. Often this is very big and we want to kind of work with much smaller data. And also not every single pixel in an image is actually informative and tells us something about what is in the image. An embedding is often something that is just a lower dimensional representation of this image. So let's say we compress our image into just a single vector of 32 numbers, and we reduce our data dimensionally drastically from 64 times 3 to only 32. All the while, we hopefully recover the most important information about what is in this image. Now, obviously, with images, they're very high dimensional. We often go into lower dimensions. Location encoders are exactly the other way around. The input to a location encoder is just a single latitude, longitude coordinate. And so we actually want to get to a bigger embedding space here, right? So we project that up towards, again, let's say 32 dimensions. This is a way to think about an embedding. And embeddings obviously need to be learned somehow. And this is the other component of Satclip that I'm happy to talk about if we're at this point already.
Yeah, that'd be great. And firstly, I just want to say I appreciate you sort of walking us through the idea of embeddings. It is a key concept, I think, regardless of what field you're working in, but especially in geospatial. I think the more times people like me hear it, hopefully, the more sort of solid it becomes in our minds. But for me personally, this is definitely a concept I need to hear again and again and again, different ways of explaining it. So thank you very much for that. So how do we create these embeddings? We mentioned images and we mentioned locations. Maybe you could walk us through the actual process of creating this embedding space.
Yes. So the embeddings for both the image and the location are obtained in a pretty similar way, and that is using a neural network. So in the image encoder component of Satclip, you feed in your image. It goes through a few layers of neural network, and then it returns the embedding in the embedding space. The embedding space of Satclip is actually not 32 characters long. It's 256 characters long, but it is still a flat vector. You don't have this kind of the matrix shape of an image with the kind of 3 red, green, and blue channels. It's just a single vector of 256 characters. Location encoder, very similarly, it is also a neural network, except that it projects it up into the same 256 dimensional space. Now, these neural networks obviously need to be trained somehow, right? At this point, they can project into an embedding space, but the projection is not meaningful because the neural network weights are not trained yet. And so now comes the component in how do we train Satclip, and how do we train both of the image and the location encoder simultaneously. And for that, I think the intuition is actually quite simple. And the intuition is that if we look at a specific satellite image, we might have some idea of where on the planet that image is. Let's say you have a satellite image that shows you some lush tropical forests, right? So some sort of rainforest. You will be able to tell from the satellite image, hopefully, that there's quite thick vegetation. It looks like it's a very wet climate. And immediately, what your mind will go to is that there are only specific climate zones on the planet that this image could fall into, basically equatorial areas. So you're already quite constrained in the kind of places around the world that you could place this on, basically specific latitudes. And now think of the picture of a desert. There's only certain areas around the world that are so dry that you can find deserts there. And so immediately you're also kind of location constrained. This is really the idea of Satclip. We try to match a satellite image with the corresponding location. So at each training step, we show Satclip both the image and the location encoder. We show them a large number of images. Let's say we show them 500 images and 500 corresponding locations. Those are randomly shuffled, so they are not matched currently. We feed our image through the image encoder and obtain the 256 character embedding. We feed the locations through the location encoder, obtain a 256 character embedding. And then we compute our loss by comparing what location embedding does the model think an image embedding belongs to, and vice versa. And this is how we train our neural networks. We can then compute the loss, and we can minimize that loss to get better and better at matching these location and image embeddings.
Wow. I guess right now would be a great time to understand like what data are we using for this? We've talked about bands and a little bit about resolution, but what is the actual platform that is generating this data that is being used here?
Yeah, so for the current iteration of Satclip, we create our own data set. We randomly sample 100,000 Sentinel-2 satellite image scenes. So Sentinel-2 is an optical Earth observation satellite that captures multispectral satellite images. So we have 13 input channels. So in addition to the red, green, and blue channels of natural images, we have other frequencies like near-infrared captured there. And we sample our data set uniformly over all landmass across the planet. So that means that hopefully every region in the world is represented. And we also sample our data set uniformly over 2 years of time, which means that ideally we'll have all seasons represented in the data set.
So with those 13 bands that you're talking about, what are we actually embedding here? Because it's got to be more than the visual representation of the landscape.
Yeah, that really comes down to the key question, right? So as you train Satclip, what sort of features are extracted from the image and then aligned with the location embeddings? So basically, what features are transferred from the image encoder into the location encoder? And this is a question that we only have the answer to some degree. And I think, again, the way to think about this is about these unique location characteristics. Think about an image of Paris. What in a satellite image of Paris are the things that make it look unique? It's not like a generic house that will make you think of Paris. It's specific features in the image. It's the Eiffel Tower or the Arc de Triomphe that will make you think, this is probably Paris. Paris is a kind of easy example because there you do have these very visually unique features that you can't find anywhere else of the world. In the example I gave earlier of the desert, there are actually many different candidate locations that would fit with that desert. And so the kind of uniqueness of a location is actually not the same across the world. There are many regions in the world that look quite similar to regions that are very, very far away.
I was wondering if you had the answer to that question, or so if you looked at these embeddings and say, okay, like in this area, in this region of the world, the thing that makes this image unique are these group of pixels in this band, for example. Is there a way then that you could use that information just to reduce the search space from the start instead of looking at all of the pixels? Focus in on, okay, we're actually in this part of the world, the thing that makes a difference is, these 3 bands or these 4 bands as opposed to these 13.
This is a great question, and this is one that we currently do not have the answer for. What this touches upon is quite related to what people are researching in large language models right now, and this is something called scaling laws. So in large language models, people talk about scaling laws when they talk about if we give a GPT-4 another 6,000 books, how much better will it perform? In satellite image models, we can think about this quite similarly, right? If we give the model one more satellite band, how much better will it perform? And then we can also marginalize out specific bands to see how important they are. In my opinion, this is pretty much an unanswered question. We currently do not know which bands are most important for these kind of self-supervised pre-training procedures like Satclip. We do know that specific bands are important for specific biological processes, right? So if we think about vegetation indices, these usually rely very specifically on some reflective bands. But this kind of domain expertise and integrating into neural networks is a lot of work and is a very active area of research.
Yeah, that makes a lot of sense. It'll be interesting to see what people came up with in that research. Do you know of anyone who's working on that at the moment?
I know that my close collaborator and co-author on Satclip, Esther Rolfe, is really interested in this. I don't think she has a paper on this yet. And I'm trying to think if anyone else is actively working on this, but I don't think so. We've definitely identified this as a potential future work area for us in the Satclip team.
Yeah, the reason I ask is because at the moment there's a lot of talk about foundational models, and I realize we're moving a little bit away from Satclip at the moment. But yeah, my understanding of it, it feels like people are just like, let's put all of the data in there as much as we possibly can and assume that that'll make things better.
I mean, scale is certainly one thing, but I think especially with Earth observation data, there's 2 caveats to this. The first caveat is that we have too much data, right? So again, if you compare to large language models, in large language model research, we're actually running out of data, right? So OpenAI has basically fed every single piece of digital text that was ever produced into their models, and they can't add more text because there is none. And so they have been relying on things like auto captioning YouTube videos to get more text. In the Earth observation space, we have the opposite problem. We have, so to say, too much data, right? We are on a petabyte scale of satellite images. We produce terabytes of new satellite images every single day. And no GPU that we currently have is able to process all of this data. That is kind of one restriction. The other caveat that I want to bring up here is that text, again, making the comparison to language models, text is much more information dense than satellite images. And a quick example here is that if you think about a satellite image of New York versus a satellite image over the Northern Pacific, they will be exactly the same size, right? So they will have the same number of pixels, height and width, and they will have the same number of channels. Let's stay with Sentinel-2 and say it's 13 channels. However, the image over the Pacific Ocean contains very little information. You might get a little bit of a signal of, is there like certain plankton in the water? Is there an iceberg or not? Whereas the image over New York contains a whole lot more information, right? It contains streets, it contains buildings, maybe trees, maybe ships that are swimming in the Hudson. And so both of these images are of the same size, but one has much more information than the other. And so first kind of getting to a point, I think that echoes a little bit the point you made earlier of kind of selecting what parts of an image are important and which areas actually provide a lot of information is also a challenge that we haven't really overcome yet.
Thank you very much for that. And again, I appreciate that we're coming a little bit away from the main topic of conversation, which is Satclip. But I think this is important. I think it adds context. And hopefully it gives people an understanding of where we're at the moment and some of the challenges that we're facing. Just before we move on and talk about use cases of Satclip, what can we use this thing for, it's probably important for people to understand the scale of these things. So we talked about this two-dimensional lat long location that we can put in and get an embedding back from that. Where does that lat long come from? Is it the top right-hand corner, left-hand corner of the image? Is it the centroid? Are we actually talking about a bounding box? And what is the scale of the images that we're using? And my guess is by answering that question, we'll also understand like the kinds of features that we can see that will be recorded in the embeddings that are created.
Yeah, so again, great question. The location that we assign to each image is the centroid of the image. We do not use the bounding box because the locations would be so close to each other that they barely have any difference in embedding space. So it's completely fine to just use the centroid. Now, the images are Sentinel-2 images again, which have a 10-meter ground resolution. So every pixel represents 10 meters. And they are 256 pixels high and wide. So 256 times 10 meters, which is about 2.5 kilometers. So that's the kind of size of the images we have.
So what does that mean for the features that we can expect to find in the embeddings? Are we local? Are we regional? Are we global scale features?
Yeah, this question is both related to the ground sample distance, so the kind of 10-meter pixel resolution, but it is also related to how many images do we sample over the whole world. And we sample 100,000 images over the whole planet, which I didn't do the full calculation, but basically the average distance between each image and the nearest neighbor is 50 plus kilometers. It's probably closer to 100 kilometers, so quite far away. And what that means, together with the general restriction of the ground resolution, is that Satclip in its current forms captures macro geographic features and not micro features. And I will give examples for both, right? So what Satclip definitely does capture is changes in climate zones, which are visible from satellite imagery, changes in elevation, which are visible in satellite imagery, and general patterns of human settlement, like a city. It will be able to capture that. And when I say structure of human settlement, I mostly mean density of human settlement. What Satclip does not capture is basically anything that happens at the sub 5 kilometer scale, which is stuff like urban sprawl, specific farmland delineation, stuff like that is not captured by Satclip, but it's also not its purpose. It's supposed to more capture these kind of big macro features of the planet.
So if we wanted to capture things in more detail, could we use the same methodology? The same techniques?
Yeah, so that's another open research question. In theory, we can train Satclip on much more data and with higher resolution to also capture these local features. Even with just Sentinel-2 images, we can capture a lot more things that are visible on the scale of Sentinel-2, right? It's 10-meter ground resolution, but you will be able to capture things like retreating glaciers or urban development from Sentinel-2. All these are things that Satclip currently does not capture. In order to get there, though, we would need to train much bigger models. We would need to massively increase our location encoder so that it can actually contain these very regional patterns all within one model. Or alternatively, and this is something we're eyeing more closely right now, we train regional Satclips, right? So the current Satclip is trained for the whole planet. But obviously, you could train a version of Satclip that is just focused on one country or even one state.
That would be really interesting to compare those two as well once they're done. So people hopefully will have a sort of overarching understanding of what this thing is, what Satclip is, and also how it was created and some of the challenges along the way and the ways we could scale this up if we wanted to. I guess the open question for a lot of people listening to this now is, great, so what are the use cases? We've mentioned some of them, but I think it'd be worth sort of diving down in a few more of these. Do you have any that you could share with us?
Yeah, I think I have two very practical ones that I can walk through. Yeah, let me start with the first one. And the first one is that you can use Satclip location embeddings as an alternative to raw satellite images in a predictive modeling task. And this application is especially interesting if you're in a low resource environment, right? So if you don't have a big GPU lying around that you can train big transformer models on for your image data set, or if you actually want to do computation on an edge device like a smartphone. Once Satclip is trained, and Satclip, maybe to take a step back, Satclip is a big model because Satclip uses a very big vision encoder to extract these features from satellite images. But once Satclip is trained, you can basically throw out the vision encoder and just use the location encoder to obtain location embeddings. And the location encoder itself is really small. It's only a few megabytes. It's a few layers of neural network. And so it can actually fit quite easily on a smartphone. Let's get back to our predictive modeling setting. Let's say we want to predict, crop yields from satellite images, but we really don't have a big data set of satellite images. And we also don't have a GPU to compute with these satellite images. Instead, we can just, at each of our locations where we have labeled data for, we take the Satclip embedding and use that instead to train a predictive model. Since the Satclip embedding is only 256 characters long compared to a much bigger satellite image, this will be much easier and much faster. Obviously, you will lose some precision over all the information that is contained within the big satellite image, but you will still, to some degree, be able to approximate the performance. That is the first application. I want to pause here quickly in case you have any follow-up question on this.
No, not at this stage. That was brilliant, thanks. And I appreciate you bringing it back to the idea of big models. That was a misunderstanding on my side. My understanding before we started this conversation was that Satclip was relatively small, and I guess a piece of it is. But at least what I heard from you then is if you look at Satclip as a project, it is still a big model.
Yeah, so the location encoder component is really small. The vision encoder component is not very small. But still, I think in the big picture of foundation models, Satclip definitely is a small model. We can have a whole different conversation on the size matter. Is that everything? Yeah, I think I can say this pretty freely. I think that as a research community, as a AI industry community, we are kind of overfitting to big models. I think there's a lot of impactful work to be done on small models, on regional models. And I think that's why I want to bring it back to examples in low resource settings, right? So this kind of study that, or this example I was giving on using only the Satclip location encoder in like low resource settings and on edge devices, this is something we're exploring actually a little bit with Microsoft AI for Good Africa, which obviously is interested in those settings. They don't have the big GPU racks that the startups in Silicon Valley have.
With that location encoder, like in low resource settings, I think you referred to it as, or perhaps on edge, where this kind of compute was happening on device. Would this work with visual navigation? Is this like an idea that you could put into a visual navigation methodology?
With visual, do you mean like geolocalization of an image?
Yeah, I'm thinking maybe a drone, a robot is moving
Yeah.
around the world.
Yeah.
And instead of relying on GNSS, we could use this as a way of like, well, where am I exactly based on this image?
Yeah, 100%. This is a potential application. We have seen a model recently that came out called GeoClip that does this localization specifically for natural images, so images that you snap with your cell phone. They created a model that basically does the same thing that we do with Satclip, except for natural images. And that model is really good at, given a specific image, where on the world is that. And Satclip can also do that. And since you can take the Satclip location encoder that can tell you roughly pretty well where in the world you are, and since that is quite small, you might be able to actually help with the navigation tasks. Yes, that is certainly an application that is possible. We have not explored it much though.
Okay. So, sorry, I got on your way of your second example there, but I appreciate that little sidetrack. That was interesting.
Yeah, no problem. Yeah, I can jump into the second example. The second example relates to one of the most beautiful properties of Earth observation data, and that is that we actually do capture the whole planet. In machine learning and AI, we often have the problem that we train our models on a specific training data set, but then we want to deploy our model, what we call out of domain, on unseen data that we have no experience with. And so models can sometimes fail because they don't truly generalize to everything in our data distribution. Now, with our planet, we know our planet is bounded, right? There's a restricted space that confines our planet Earth. And we actually covered that whole space using Earth observation satellites. So at least in geospace, we don't have this out of domain problem. Everything is seen. We still have an out of domain problem when we look at the time dimension, of course. We can't look into the future. But in space, we see everything. And I think this is the other big potential of Satclip and also, to be honest, other GeoFoundation models. And that is that you can help ground potential downstream models and their applications. And I can quickly explain what I mean by that. Think about an example scenario where you want to do some segmentation task on satellite imagery, like you want to extract all building masks from a satellite image. This is a task that is very often relevant in industry settings. Now, let's say that your training data is in a specific region of the world. Let's say it's in the US, right? So you have satellite images for the US and you actually have the segmentation mask that you want to train your model. That segmentation mask was probably hand labeled by a person in a lot of work. Now, buildings in the US will look a very specific way, right? They're usually rectangular, they're very well spaced out in rectangular streets, and they're somewhat separated from one another. Now, this model you might want to transfer to a completely unseen area. Let's say you want to transfer it to a country in Africa like Somalia. What you kind of implicitly assume is that buildings in Somalia look the same as in the US. And of course, we know that that is not true. So buildings in Somalia are not necessarily rectangular, they're much smaller, and they're not well spaced out and gridded. So we run into a problem. Our model can fail very easily on this. And this is where these Earth Foundation models come in that are trained without any labels, right? So Satclip was not trained on any labels, but it has seen data from both Somalia and the US. And what Satclip location embeddings, again, learn is similarities between different locations on the planet. And what we can do then is we can exploit these similarities. We can basically, if we integrate Satclip location embeddings in segmentation models, at test time, we can look which parts of a training data set look visually the most similar to what we're currently trying to do in the test set, and then take the weights from the model that correspond to these kind of features that we see in the test set most, and then get hopefully a better prediction. And this might sound like an abstract example, but this is actually something we're currently testing that seems quite promising.
That sounds really interesting. You call it grounding there, but I'm pretty sure it sounds like a concept that we were talking about earlier called geographic conditioning. Is that correct?
That is correct. Another word for it is a geographic prior. And again, the idea here is that the geographic information, be it the raw latitude, longitude, or features at this latitude, longitude, that they will tell you about something about the problem that helps you with your decision making. The easiest example of this is image classification of animal images that are taken with a camera trap, for example. Take an image of an Arctic fox. It's a white fox. And if you just take the image, classifying that will get you only so far. But as soon as you add location, you know that Arctic foxes can only be found in certain latitudes, only in the Arctic. And so the location actually provides a ton of information to your classification problem. And this sort of geographic prior that you derive from this geographic conditioning, will make your model much stronger. Satclip has the same idea.
Wow, that makes a lot of sense. Did you say you're currently working on this? Like, is there any chance, can you put some numbers around, like, okay, before we used this general model and we got this result, and after, using Satclip and this idea of geographic conditioning, the result improved by X? Is there any sort of way we could, or could you maybe help us set some expectations on how much better it would be after using this?
I cannot currently give numbers since this is work in progress. And even if I could talk more about it, I would feel bad because we're not at a stage where we have like really reliable numbers. But I think I can give a visual example of what the difference will look like. And I want you again to think of like a dense cluster of houses in Somalia and our model that is trained on the US. Basically, a model that is not trained using Satclip, just purely a segmentation model based on US satellite images and building masks, will be able to draw a boundary around this dense cluster of buildings in Somalia quite well, right? So it will be able to define the outline really well, but it will not be able to disseminate individual buildings within the cluster. And this is something that Satclip will immediately help with, right? So Satclip will be able to tell there's smaller structures within this big data set. And so the model will start at least to find these smaller structures. It will not completely overcome the problem. This is also not something that the current iteration of Satclip was trained for, but it kind of shows a promising direction. This is not a number, but hopefully it still gives a little bit of an intuition of what Satclip is helping with.
It does. That was really useful. I think that when we have more research around this stuff, it'd be really interesting to compare these sort of global, perhaps, my words, not yours, general models against specific models, like a model designed for Somalia, a model designed for, I don't know, the continent of Africa versus North America, for example. That'd be really interesting to see which one is actually doing a better job, and then sort of weigh the costs. Okay, well, does the law of diminishing returns kick in at some stage and make the more general model, well, because we can apply it to all these different other situations, this is actually a better solution for us?
I'm fascinated by that question. I think it's one of the big questions of GeoAI right now. I mentioned Esther Rolf already earlier. She's one of my closest collaborators. I hope you have her on the podcast at some point because she thinks about this question a lot. And she has a paper in the works that's hopefully out soon that tackles this question a little bit. And I actually think, again, as a GeoAI community, we have to maybe take a little bit of a step back from the kind of foundation model push and these big global models that we want to build and look at if they're actually useful. And I feel like in many scenarios, local models might be much, much more useful, or global models that are, presented as if they can work on anything will actually break when deployed in very localized contexts. And that's a bit of a bitter lesson. But I think to me, it's also at the same time very motivating because I don't think that tells me that we should stop working on big global models. It tells us we should get better at them. But it also tells me that there's still a niche for people who don't have 6,000 GPUs and can train these huge foundation models. But there's still a space for people who build very purposeful, localized, and specific models.
It'll be really interesting to see how that plays out. One of my next questions here was going to be like, what is the future of Satclip? And where are we going? What are we going to do? But perhaps the future of Satclip is also the future of these foundational models when we think about GeoAI. And I wonder if there's going to be any lessons we can learn from when we look at large language models, for example. So at the moment, we're within the market is saying, yes, great, ChatGPT, GPT-4, when GPT-5 comes out, awesome, and we've got these other models. But the push is not just to use those models the way they are. I think all the really interesting applications are being built on top of them, where they're sort of channeled into a specific area, a specific silo, and said, this particular quote-unquote chatbot is going to be amazing, is going to outperform the general model in this thing, at reading scientific journals or writing about what QGIS could do, for example. I wonder if there's going to be any sort of parallels that are drawn between what we see happening in large language models and this explosion of applications being built around them and on top of them that are much more specific, and the same what we're going to see in the GeoAI world.
I'm really curious for how the next years are going to play out. And I think a lot of that is really down to, funding decisions and not necessarily to what is the most promising, at least in my eyes. First off, I think that Satclip has some implications generally for GeoAI. And I think that is the idea of fusing together different data modalities through the geo information. Satclip does not do that yet. We only use one input modality with the Sentinel images. But at least in theory, you can think about the multi-model Satclip that takes in satellite images, but also geotech tweets, geotech natural images, and then derived products like an elevation map, and fuses them all together through the geo metadata into one location encoder. So this kind of fusing of different geodata modalities is one thing that I really have my eye on, and that might help us overcome this big multimodality problem that we have with geo information.
That would be really interesting. I was thinking about a DEM, for example, because earlier on we're talking about like if you can look at a landscape and say, oh, there's some mountains over there, perhaps that's the Rocky Mountains. That's a very visual thing. And that would stand out in a digital elevation model. You know what I mean? And I was wondering if that would add a lot of, not context, but a lot more information to the embedding space. And also when you're talking there about tweets, I'd never thought about the idea of adding geolocated text. But I wonder if something like Wikipedia, georeference Wikipedia articles would be of interest.
Yeah, so first on the elevation map, I think in the case of the Rocky Mountains, the elevation map will not add much information. But think about the example of deserts, right? So currently Satclip is not really able to disseminate different deserts. But obviously different deserts like Sahara, Atacama, or Gobi Desert, while they might look visually similar, they're all at very different elevations. And so this is an aspect where elevation could come in. And yeah, I would agree, like text modalities like tweets or Wikipedia would be very interesting too. The question again is in them is like how much unique location information is in a tweet. If the tweet is just, I just had a taco from Taco Bell, that does not tell us where this tweet is from, beyond that the tweet was sent in English and is probably from an English-speaking region of the world. So there are all these kind of intricacies we need to think about. But I think if we fuse modalities together through location, we can probably learn some sort of fused together location embedding that explains to us all we know about a given location.
Slightly off topic, but also related. Years ago, I was talking to a researcher at the height of the COVID pandemic, and he was working with billions and billions of points, looking at telemetric data from apps that people were carrying around, looking at movement and the spread of the disease and that kind of thing. And he was doing some really, 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 really interesting work. I'm not trying to take anything away from him, but it was interesting. In the end, he said, well, it came down to like we could almost have got the same results just looking at like who has the money. Where are the rich people? Where are the poor people? Oh, rich people are less likely to be affected by the pandemic than the poor people. Of course, I'm massively generalizing. But it was really interesting, all of that work and all of that, these billions of points that he'd been looking through, and it came down to, oh, you know what? Actually, it's all about a lot of this data that we already know. We already know who was rich. We already know who was poor. And these people were affected differently.
Yeah, I think that is exactly true. There's a lot that we currently are not using and could be using. And there's a lot of kind of very straightforward ways of using data that often fall a bit flat, especially when the hype is all about foundational models. I also wanted to get back to your question about comparing, like basically getting lessons from LLM research in the last years. Is that a good time now, or should we skip that?
No, please. I'd love to hear your thoughts.
Again, I think there's some lessons we can learn, and in some ways the domain is just too different. But I think the one lesson that I think we can see from the last 3 years, maybe in large language model research, that I think definitely applies to Earth Foundation models like Satclip, is the lesson on data selection, data quality, data processing. Kind of very popular paper over the last years was a paper actually from Microsoft called Textbooks, It's All You Need, that basically shows that instead of training your large language model on all of the internet, including all of the trash you can find there, but training it on very, very high quality data, for example, science textbooks, your model will immediately be much better. And I think this is a very, very similar lesson that we can apply to geospatial data. And so how do we select the images, for example, that go into Satclip? Obviously, we want geographic diversity, but we also want diversity in socioeconomic, demographic aspects, climate zones, all of these kind of characteristics. And so in many ways, it comes down to a sampling problem and to a data selection problem that is a completely open field of research and super exciting.
I just want to ask you one final question here to wrap up the conversation. And should we be thinking about these kinds of models like Satclips, as digital twins?
The marketing person in me would say yes. The scientist is a bit more cautious. I think that the ambition of Satclip, thinking many years in the future, is that, yes. And with that, I mean that through this kind of location image matching task that we do with Satclip, if you expand that a little bit to location and time image matching, what your neural network, your location encoder, hopefully will learn is certain physical properties of our planet, and ideally also periodicity and trends of our planet. And what I mean with that is, ideally, a big enough, highly scaled, optimized Satclip should be able to recover certain physical processes of our planet. And that includes seasonalities like winter and summer, but also long-term trends like climate change. Now, if these self-supervised models are able to recover those trends from data purely, that will mean that they have learned some physical properties of our planet just from data alone, without us giving them any physical laws or other structures that we already know of our planet. And if we think that even further, these models might be able to extrapolate these trends into the future. And then this is where we enter the digital twin domain, where we can think, can big Earth Foundation models that recover these kind of trends of planetary dynamics, can we use them to simulate future conditions on the planet, maybe conditional on stuff like carbon emissions or so? And can we then use those to, test scenarios, test policies, test interventions? I want to make clear, though, that this is very much a research ambition that we might work towards to, but at this point, it is but a dream.
That was absolutely perfect. What a great way of rounding off the conversation. Thank you very much. People listening to this, they might want to reach out to you. If that's the case, where can they do that? What's a good place, or where can they go to get a hold of you, to learn more, to try this out for themselves?
You can just go to my website, Konstantine Klemmer, so first name, last name, .github.io. There you can find my contact information, like my email. You can also find Satclip on GitHub. So if you just Google GitHub and Satclip, you will find the whole Satclip model. We have some interactive tutorial notebooks there that should hopefully allow you to easily access the models, play around with them, and understand a bit more what they're doing. All the pre-trained models, including our data set, are freely available for you to download and play around with.
Wonderful. I'll put links to those things in the description of this episode. Thanks again, Konstantin. This has been brilliant. Cheers.
Thank you.
I really hope you enjoyed that episode with Konstantine Klemmer. I'll put a link in the show notes to his LinkedIn page, and there'll be links where you can find out more about Satclip if you're interested. I'll also link up a few of the other podcast episodes that are related to this one. So well worth checking out the show notes today. There'll be a few different links in there if you're curious about learning more. Okay, that's it for me. That's it for this episode of the Mapscaping podcast. I'll be back again soon. I hope that you will take the time to join me then. Bye.